Hello, hi Vanida. Can you please confirm? Am I audible or not? Oh, hi. Thank you. Okay, then let's start. Let's wait for 2 more minutes. Then we'll start. Yeah. Okay, then let's start. So yeah, good evening all. My name is Rituraj Singh Sejawat. I am Primary Research Fellow in Department of Earthquake Engineering, IIT Roorkee. This is the interactive course of the course NOC 24C85 Finite Element Method and Computational Structural Dynamics, which is currently being tutored by Professor Manish Khande, who is Professor in Department of Earthquake Engineering, IIT Roorkee. So this is a 2 hour session. So those who are coming for the first time, let me introduce what is the purpose of this particular session. So in this 2 hour, basically we'll be interacting with our learners of this particular course. Also we'll be discussing some of the important concepts which will be required to solve the assignment problems. Along with that, we'll be solving some of the sample questions related to this particular topic. We will also be involved in some of the doubts concerned with this particular session, and any other query related to the course, we are going to discuss it. So this all are the objectives of this particular sessions. So let's start. So till now we have deal with the finite element concept of 2 dimension and 3 dimension, and we have solved some of the examples also. So earlier we have solved example for 4 noded element, and we have also tried to abstract the stresses at stresses and strains at various gauge points of that particular element, and then we have also tried to extrapolate the stress and strain of that particular node to the element. Now the next part is we are going to do is related to the mapped elements or the elements which are of the curve shape. So let's assume that if you have a curve shape, so how you are going to deal with it. So in general, when we come to the computational part, there is no uh, perfectly algorithm which can define what should be like to define a particular curve. So to define any particular curve, we usually discretize the whole curve. That curve will be made up of various line elements which are of very small size, and will constitute them and connect them each with each other in such a manner such that it form a particular segment of that circle. So that is the whole idea. So for quadrilateral elements, like these are the particular elements we are going to deal with. So this, for that particular case, we also need to deal with the Jacobian, uh, which is a particular component to map the linear elements to the curved elements, or the curved element to the linear elements. So we are going to use the concept of the isoparametric map. So where we are going to define our coordinates or lines in some form of the parameters to map them. Let's say in our case, when we are going to map the circular segments into the linear segments, or vice versa. So concerning with the same question, let's start with our lecture sample questions with it. So in front of you, you are having two quadrilateral elements given here, and you need to determine the Jacobian at point xi equals to 0 and eta equals to 0 in each case. So please start with this particular part, and that's all. So first one is the 4 noded element in front of you, and then another one is the 8 noded serendipity element availability. So those who came late, just read the question. So you are having a four quadrilateral elements shown in the figure below. You need to identify the isoparametric mapping from the xi eta coordinate to the xy coordinate, and accordingly you need to find the determinant of the Jacobian at particular point xi equals to 0 and eta equals to 0 in each. So let's look to the question. So usually for isoparametric mapping, you have been given with the element as shown below. So answer there for isoparametric mapping. first what you will do, you will define the shape function. For given quadrilateral system, so how to find the shape function? So for this particular quadrilateral system which is available with you, four-noded quadrilateral system, which is 1, 2, 3, 4, 0, 2, 3, 0, 5, 1, 3, 3.5. Okay, so the isoparametric system which is there in front of you is this. So this is 4, 3, 2, 1. So this is the corresponding quadrilateral in your another Cartesian system. So this is minus 1, 1, this is 1, 1, 1, minus 1, and this is your minus 1, minus 1. Okay, so next is you need to find the shape functions. So how to get the shape functions? So shape functions as given, we can find it as n1 is equals to 1 minus xi upon 1 minus meta is whole divided by 4. Then you have n2, which is 1 plus xi 1 minus meta whole divided by 4. And this is n3 1 plus xi 1 plus meta whole divided by 4. Then you have n4 1 minus xi 1 plus meta whole divided by 4. Okay, so with the help of this you are having 4 shape functions available with you. Then you need to define the coordinate vector. x1 y1 x2 y2 x3 y3 x4 y4. Okay, this is the coordinate vector. How much is this? So you need to mark this particular coordinates into this vector. So what is there in front of you? 0, 2, 3, 0, 5, 1, 3, 3.5. So this is your coordinate vector. Once you have this particular thing, then you have to do the geometric mapping. So for geometric mapping, what we're gonna do, this is x, y, then you have to define the matrices for the shape function. So 0, 0, then you are having n1, n2, 0, 0, n2, 0. So I'll write it again, the shape functions which are there with you. Sorry guys. Yeah. So for getting the isoparametric mapping, this is the particular function we use, where you will be having the shape function, 0 and 2, and 3, 0, 0 and 4, 0 and 4, and then we will be having the coordinate vector availability, which is 0, 2, 3, 0, 5, 1, 3, 3, 5. Once you'll have this, the final expression for xy, that's uh, mapping in another coordinate in xy of our interest, will be given by, so the final answer I'm having with me. So in the terms of the neta and xi, this will be the values available with me. So minus neta minus 5 into xi minus 5 neta minus 11 by 4 minus neta plus 9 xi minus 5 neta minus 30 by 8. So these are the other things. So finally we got the coordinates in terms of the zeta and 9, zeta and xi and neta, and once you have that, you can calculate the Jacobian matrix. The Jacobian matrix is given by dou x by dou xi, then you have dou x by dou neta, dou y by dou xi, and dou y by dou neta. So this is your particular Jacobian matrix. Once you will have that, this will give you the Jacobian. The answer which is there with me is, so you are having the xy, So this is your particular x and this is your y. Once you will get this, you can take the partial derivative of each coordinate x and y in terms of zeta, xi and eta. This is also xi and eta, and once you have that, you can calculate the Jacobian. So the Jacobian which is there with you is 5 minus neta by 4, 5 minus xi by 4 minus 9 plus neta by 8, and then you'll have 5 minus xi by. Once you have that, you can get the determinant of xi Jacobian. So that Jacobian which we are there with us is minus 7 xi minus 35 by 60. And what has been asked in the question? In the question it has been asked, you need to determine the determinant of the Jacobian at point xi equals to 0 and eta equals to 0 in each particular case. So for that part, you can calculate what is your Jacobian. So at coordinate x comma 0, what has been asked? At xi equals to 0 and eta equals to 0. So for that particular case, you can put minus 70 minus 35 minus 60. So the final answer will be there with you is 35 by 60. So this is your determinant of the Jacobian at this part. So which is equal to 2.17. Okay, so this was your first part. So for 4 quadrilateral element, now let's move to our another part. Where you are having 8 noded serendipity element. So similarly, you need to form the coordinate system. For that you need to write the shape function for all 8 points, and once you have 8 shape functions, and using that 8 shape functions, now accordingly you can determine your coordinate system xy, then you can find your Jacobian, and once you have your Jacobian, you can find it out what is the determinant of that particular system. So just try once this particular thing in the similar fashion. There is some difference in the shape functions, how you are going to do that. You can refer your lecture slides, else I'll let you know how to solve this particular. So we have done for this. Now please try for this particular. So let's try with this. So the quadrilateral element which is available there is 8-numbered quadrilateral element. Which is 1, 2, 3, 4, 5, 6, 7, and 8, right? And the corresponding quadrilateral system in another uh, xi and eta coordinate system. You can write it like this. So this is your 1, 2, 3, 4, 5, 6, 7, and 8. So this is your minus 1 comma minus 1, 0 comma minus 1, 1 comma minus 1, 1 comma 0, 1 comma 1, then you are in 0 comma 1, minus 1 comma 1, minus 1 comma 0, which is given by 1, 2, 3, 4, 5, 6, 7, 8. So once you have this, you can write all the 8 shape functions. So let's write it for n1 first. Let's write for that intermediate node first. So n5 is given by 1 plus xi, 1 minus xi, 1 minus eta per 2. is given by 1 plus z 1 plus meter 1 minus meter, and this is by 2. Your n7 is given by 1 plus z 1 minus z 1 plus meter by 2. Then your n8 is given by 1 minus z 1 plus meter 1 minus meter by 2. Accordingly, you can write it for now utilizing the n5, n6, n7 n. For the n1 element, the n1 shape function for particular node goes point 1. You can write it like this. So we are having n1 approximate n1 minus half of n5 minus half of n6. So how much is that? So n1 is minus n8. So accordingly, the isoparametric mapping n8 and x8. Similarly for y, you can write it as n1 y1 plus n2 y2 plus n3 y3 plus n4 y4 plus n5 y5 plus n6 y6 plus n7 y7 plus n8 y8. So once you are having the isoparametric mapping, it can be written as x comma y in terms of shape function, n1 x1, n2 x2, n3 x4, accordingly so on. So you have defined your shape functions. Utilizing that shape functions, you can write your xy, and once you are having your xy, you can put the shape functions, and you know your coordinates also, x1, x2, x3. So you will get the final value of xy. So once you have all the shape functions, you can write the isoparametric mapping, and can be written as xy n1 x1 plus n2 x2 plus n3 x3 plus n4 x4 plus n5 x5 plus n6 x6 plus n7 x7 n8 x8. Accordingly, you can write n1 y1 plus n2 y2 n6 y6 n7 y7 plus n8 y8. So accordingly you will get your final x vector, which is xy in terms of xi and eta. So the final values which are available with you. So accordingly you can put all the shape functions which you have written before, and you can write it as Jacobian in terms of weight model quadrilateral system. So the okay, I don't have the xy with me, but yeah, I am having the final Jacobian matrix available with me. So which is given by by 2 0 3 by 2 and for at xi equals to 0 when eta is equal to 0, the mode of Jacobian matrix is 3.0. So this is your final answer for the determinant of the Jacobian of the matrix. So this is your final answer for the determinant of the Jacobian. So we know how to calculate the Jacobian. So for 4-noded quadrilateral system or for the 8-noded serendipity elements, this is how you are going to evaluate. So first you need to draw a figure which is corresponding to another coordinate system, which is xi and eta coordinate system. Once you have that, you need to write down the shape function for 4-noded quadrilateral system and for 8-noded serendipity elements. And once you have that, you are going to evaluate your xy coordinate system, which is Jacob. Then you are going to find your xy system with the help of the shape functions available with you. And once you have that, you are going to write the Jacobian in the form of this dx by dx by d dou eta. So partial derivative of xy with respect to xi and eta. And once you have that, you can find the determinant of that Jacobian, and you can finally find the Jacobian at particular value of the coordinate. So for serendipity elements, this is your answer. Jacobian is equal to 3.0. So this was about the question number 1, which is about how you are going to map the element from one Cartesian system to the another Cartesian system. Now let's take a practical problem with the help of this. So you are having a 4-noded quadrilateral element, same 4-noded quadrilateral element which we so same 4-noded quadrilateral element system which we have taken in question number 1, and utilizing that 4-noded quadrilateral system, you are going to find the element stiffness matrix if the component is part of a mesh discretizing a section of a typical dam. So the question is given to you for the 4-node quadrilateral element, which is given in problem 1. You need to find the element stiffness matrix using the isoparametric formulation if the component is part of a mesh discretizing a section of a typical dam. So you need to assume E is equals to 30 gigapascal, Poisson ratio is 0.2. So accordingly, once you have this, within that solution, you need to find the element C3 of the constitutive matrix D, and this element C3, 1, 7 and 7, 7 for the stiffness matrix, and for element 2, 2 of your stiffness matrix of the element. So let's try this, and then we are going to solve. Take 5-7 minutes, and then we are going to see how to approach this type of problem. Okay guys, any lead particular part how to solve this? Then let's check the answer. So first let's see what has been given in the question. So it is a four noded quadrilateral, sorry, yeah, it is a four noded quadrilateral algorithm, and you need to find what is the element stiffness matrix using the isoparametric formulation. The E is 30 gigapascal and Poisson ratio is 0.2. So first of all, and another part is which is important to highlight, a section of a typical dam. So this is a, so it has been given to you, it is a four noded quadrilateral element. Then you need to find what is the element stiffness matrix using the isoparametric formulation. So accordingly you need to use the Jacobian in this part, and the component or is a part of a meshing discretizing. So the particular thing which you are having is the section of a typical dam. So when we say section of a typical dam, so what kind of problem we are dealing with? So the problem which we are dealing with is here is a plane strain problem. So usually in the plane strain element, uh, your strain since one length is that much used, so that in that particular length of a body your strains tend to be zero. So definitely you will be having only the strain available in that particular place. So in that typical section length you will be having the, you can model it using plane strain. So what has been asked, so usually the stiffness matrix is given by -1 to 1 B transpose B modulus of J T xi and D beta. So what is the B matrix? So for plane strain element you all know that B is given by uh, Tx, no, first you are having this, and let me check first what is that. So P matrix is given by dou by dou x dou by dou x 0 dou by dou y 0 dou by dou y, then your dou by dou x. So this is your differential operator, and once you have this, then you are going to write your shape function, which is given by n1 0 0 n1 0 n2 0 0 n2 n3 0 0 n3. Then you are having n4 0 0 n4. So this is your differential operator. You can find this is your differential operator, and this is your particular matrix comprising of your shape function. So this is your 3 by 1, and then this is your 2 by, sorry, this is your 3 by 2 matrix, this is 2 by 8 matrix. So ultimately we'll be having 3 by 8 matrices. So let's write what is the shape functions available with us. So the shape function which we have written in part 1. So these are your particular shape functions for plane strain element. Which is given there. So accordingly we need to find the derivative also of the shape functions, because this particular differential operator will perform operation on this shape function matrices, and this shape function matrix then will convert to we'll be having some differential functions of and z. So these are your derivatives of the shape functions. Let me save this because this happens again and again today. So this is your n1, n1, n2, n2, n3, n4, n3. So accordingly, your final strain displacement. So these you are known as the strain displacement relation matrix. So this is your particular strain displacement relation matrix which is available with you. So we have obtained the D matrix. Now let's see what is the D matrix. So D matrix you know is your constitutive relation matrix. So for us it's a elastic element. So your D matrix is given by 1 plus mu 1 minus 2 mu, so 1 minus mu 0 mu 1 minus mu 0 0 1 minus 2 mu by 2. So this is your particular constitutive relation matrix. So you obtain your strain displacement relation matrix. You are having your constitutive relation matrix available with you. Once you have all of this, you can obtain your stiffness matrix. Any doubt till here? Okay, then let's see. what is the next part? So once you have obtained your constitutive relation matrix, so for time being, just put the values of the constitutive relation matrix and evaluate this. The values of the constitutive relation matrix. Final d value which is available with us is 1 into 10 to the power 10, and that is 10 by 3, 5 by 6, 0, 5 by 6, 10 by 3, then you are having 0, 0, 5 by 6 Newton per meter square. So this is your D matrix available with you. So once you have your constitutive relation matrix, you can use this particular expression of Once you have this, so you got a D matrix, you know how your status matrix is given. So your so D matrix is there in front of you. Just give one more. Going to finish about 10, 10, 5, 3, 5, 5, 6, 0, 5, 5, 6, 10 by 3, 0, 0, 0, 5, 5, 4. So this is 5 by 4. So this is your D matrix. Once you have your D matrix, so accordingly the Jacobian determinant of the Jacobian which you got was -7, right? -35/16, right? This is the Jacobian which you got. This one. So once we have this Jacobian, so accordingly now your the stiffness matrix which is given by is your K times thickness -1 2 +1 B transpose determinant of B means you T is right by T meter, right? So you have your B matrix available with you. You are having your B matrix available with you. Jacobian you know is -7 by -35, and so you can evaluate what is your P. So we are going to use 2/2 Gauss quadrature rule. So your stiffness matrix can be written as P -1 2 +1 B transpose T of P of J T xi by T meter, right? So this thing we can evaluate using 2/2 Gauss quadrature rule. The integral So accordingly, the stiffness matrix is evaluated at 4 cross points. So for kg1, you know your B matrix, right? You will be getting the kg1, kg2, kg3, kg4. So kg1 will be your bg1 transpose d into bg1 times your Jacobian for the first coordinate, for first point. Accordingly, for second we will be having bg2 d bg2 Jacobian for the second coordinate. Then we will be having for third coordinate g bg3 Jacobian for the third coordinate. Then we will be having bg4 transpose b bg4 Jacobian for the fourth coordinate. So for all these four ghost points, you need to evaluate your stiffness. Once you are having your stiffness evaluation at all the four ghost points, then you can calculate what is your kg1, kg2, kg3, kg4. Okay. So for this part, you need to consider xi eta for the first Gaussian point, then for this for the second Gaussian point, this is for the third Gaussian point, and this is for the fourth Gaussian point. So you will get this, and you will be having the four, all four, j1, j2, j3. So your xi eta you need to consider for all the corresponding four. B matrix, your xi and eta will be corresponding to that particular Gaussian part. D is anyway the material matrix, so it's same. So this is how you're going to evaluate kg1, kg2, kg3, kg. So once you have this, your final stiffness matrix, so your final stiffness matrix will be given by k is equals to 1 into kg1, 1 into kg2 plus 1 into kg3 plus 1 into kg4. So this is will be your all four stiffness matrix which is going to available with you, and that will give you the what is your final key. So once you have this K matrix, so what has been asked in the question? So once you have been, so in the element 3 of the constitutive matrix, so you have already written constitutive matrix, so this is your element 3. Then element 3 will evaluate with nodes to the nodes 1, 2, 3 respectively. So this 3, 3, 3, 1, 7 and 7, 7. So 3, 3 is in this matrix, 1, 7 in this matrix, and 7, 7 in this matrix. and once you have all the pros cons, so accordingly for the stiffness, final you can evaluate using this one into kg1, 1 into kg2, 1 into kg3, 1 into kg4. That will give you the element 2 of the stiffness matrix. So this whole calculations, doing the hand calculations will be difficult for you. So I do suggest you guys either use the Octave and MATLAB for that. So matrices operations are a bit easy if you perform those matrices operations in the in this particular using some numerical tools, and so that you won't struggle with the calculations. So that was the last question for today. If you guys have any doubt, please shoot up. We can discuss this. If you have any doubt regarding your coming assignment questions, please feel free to ask. Or if you have doubt in our today's session, then also you can ask. Those who are watching this video at the later end through the YouTube channel, you can post your queries in the comment box. Definitely I'm going to address that. So, and you can also post your query in the discussion forum. So our other TAs will be available for you to address your question in that part. Please take 5 minutes time. Just check with your assignments. If you have any doubt, we can do that. If not, we can. So for question solving, actually, I suggest you refer that particular book which has been suggested in the course description itself. So, or you can refer two books more. So, am I audible, Aishwarya? Hello. Aishwarya, I think please check at your end because other listeners are able to listen. Am I audible now? Yeah. So Aishwarya, what I'm saying that you can refer the book which has been suggested in the description of the course. There are some problems available there. You can solve this. I'll suggest two books by Junkovich, and the another book is by the Bath. So that both books you can check for the finite element, or you can also refer the book by the Jane Reddy. So that Jane Reddy book has described the finite element with very simple, like not simple, but yeah, it's very convenient for the beginners. So that book will be helpful in to you in understanding the things from the scratch. So that will be helpful. I'm not sure, Aishwarya, whether we can provide the PDF or not. Actually, even we are not having that. We refer the in-house books which are available in our library. But yeah, you can access it, I guess. I'm not sure, but if you are having some access to some central libraries, for example, one of the library, National Digital Library by the IIT Kharagpur. So there are some libraries which can provide you access to those books. I'm not sure whether those books are available there or not. If not, these books are available for the online purchase, so you can refer them. Was I clear, Aishwarya? Okay. You guys are getting the solutions of the assignments, right? At the end of the week, I guess. Means once you have submitted your part. So yeah. So I think those, like even that will be also helpful. Means you can get an idea means how the things are happening, and also you can refer to the solutions of the sample questions which we are discussing in our this interactive sessions. So these are the another set of questions. You can post your query anytime means in the upcoming sessions. I do understand getting the PDF, but since like from the IIT perspective of from the NPTEL team, even though we have the PDF, we are not allowed to share that uh, because due to some copyright issues. But yeah, whatever content, like if you can share, I'll check with the NPTEL team once if they allow me, like if they allow the TAs to share. So, or I'll discuss from the instructor himself. So he will let us know. So then we can provide you. But as for timing now, what I know is we are not in the position to share that. Okay, yeah, thank you, Ashwarya. But you can come up with your question anytime, please. Okay, guys. So if there's no any doubt, I think we can wind up our session today. Let's meet again on next Tuesday at the same time. So please post your query in the comment box of the YouTube section if you have any. So thank you everyone. Let's close the session.